In this lesson you will learn about differentials. And I've started off this lesson with all of the formulas that you will need depending on the wording, so you may have to refer above to reference a formula. But as we go through the examples, you will see the graphical interpretation of a differential. So for number 1, the directions are to find the linearization L of x of f of x at x equals a. So if you look above at the formulas, the formula for linearization is L of x is equal to f of a plus f prime of a times x minus a. So I will use this formula for all of the parts in example 1. So for part A, we are given f of x equals x cubed minus x at x equals 1. And the graph here on the right shows the function f of x in black. And the red is actually what we're looking for. The red is L of x. And you can see by the graph that L of x is just the equation of the tangent line at the point x equals 1. So we're looking for the equation of the tangent line at the point x equals 1. So to find that, I start by finding f of 1. And if I substitute 1 in for x, I get the point 0. Then I find f prime of x, and I get 3x squared minus 1. And if I find f prime of 1, I get the value of 2. So now if I substitute in these values into the formula for linearization, f of a is f of 1. All of these a's that you see in the formula is just this value x equals 1, so it's really a equals 1. And then plus f prime of 1 times x minus 1 f of 1 is equal to 0. F prime of 1 is equal to 2. So if I simplify this, the equation is 2x minus 2. So the equation of the tangent line is 2x minus 2. So the purpose of finding the equation of the line when we're working with differentials is on this graph here is just a zoomed in picture of the one that we saw above. This point here is x equals 1. If we wanted to approximate what the value of x equals 1.3 is equal to, instead of substituting it in to the actual function, we can substitute it into the linearization equation, and we wouldn't get an exact answer, but we would get something close to it. And since this is a zoomed in picture, you can see what the difference in the correct value would be. So for part B, f of x equals square root of x, and we start by finding f of 4, which is just equal to 2. And then to find f prime of x, I will rewrite f of x as x to the 1/2. So that f prime of x is 1/2 x to the negative 1/2, which is 1 over 2 times the square root of x. And so f prime of 4 is equal to 1 over 4. So that the equation of the tangent line is f of 4 plus f prime of 4 times x minus 4. F of 4 is equal to 2. F prime of 4 is equal to 1/4. And if we just distribute the 1/4 and then combine like terms, L of x is equal to 1/4 x plus 1. Part C, f of x equals the sine of x at x equals pi. So if I start with f of pi, the sine of pi is equal to 0. F prime of x, the derivative of sine x, is equal to cosine x. So when I take f prime of pi, cosine pi is equal to -1. So I substitute these values into the formula. F of pi is 0. F prime of pi is -1. And simplifying this, L of x is equal to -x plus pi. And for part D, f of x is the square root of 1 plus x plus sine x at x equals 0. So I start by finding f of 0. And for f of 0, we have the square root of 1 plus 0, which is just the square root of 1, plus the sine of 0. And the sine of 0 is just 0, so we're left with 1. And then when we find f prime of x, I want to rewrite f of x as 1 plus x to the 1/2 plus sine x, so that f prime of x is equal to 1/2 times 1 plus x to the -1/2 plus cosine x. And I can rewrite the derivative as 1 over 2 times the square root of 1 plus x plus cosine x. So now when I find f prime of 0, I have 1 over 2 times the square root of 1 plus cosine 0. And 1 over 2 times the square root of 1 is just 1 over 2. Cosine 0 is equal to 1. 1/2 plus 1 is 1/2, which is 3 over 2. So the equation is equal to 1 plus 3 over 2 times x minus 0. And if we write this in slope-intercept form, L of x is equal to 3 over 2x plus 1. So let's look at some different types of differential problems. So in number 2, we want to use the information to evaluate and compare delta y and dy. So if you look above at the beginning of this lesson, you will see the formula for delta y. Delta y is equal to f of x plus delta x minus f of x, and dy is equal to f prime of x dx. So for number 2, we want to use the information to evaluate and compare delta y and dy. So for both parts of this example, we will use the formula for delta y in the beginning of this lesson, which is f of x plus delta x minus f of x, and the formula that we will use for dy is equal to f prime of x dx. So let's start by finding delta y, then we'll find dy, and then we'll look at the graph and I'll show you what the graphical interpretation is of delta y and dy. So for delta y, we have f of x plus delta x minus f of x, and if we substitute the information that's given to us, we have f of 1 plus 0.5 minus f of 1, and so delta y is equal to f of 1.5 minus f of 1, and to find f of 1.5, we just take our function f of x, which is x squared, and f of 1.5 squared is 2.25, and f of 1 is equal to 1. So I take these two values and substitute them in, and the answer for delta y is equal to 1.25. Now we look for dy. And again, the formula for dy is equal to f prime of x dx. And to find f prime of x, I just take the derivative of f of x, so it's 2x. And so f prime of 1 is equal to 2. So dy is equal to f prime of 1, and then dx is not given to us. But dx is always the same as delta x, so if delta x is 0.5, dx is 0.5. So dy is equal to f prime of 1, and f prime of 1 again was equal to 2. So dy is equal to 1. So graphically, our value of x was x equals 1. So 1 is here, and the y-coordinate that corresponds to it is also 1. Since our delta x and our dx was equal to positive 0.5, and our x was equal to 1, that means that we're approximating the value of 1.5. So the y-coordinate that corresponds to 1.5 on the actual function is right about here, and the y-coordinate that corresponds to 1.5 on the tangent line is right about here. So the distance between the function value and x equals 1 is delta y, and the distance between the point on the tangent line and x equals 1 is dy. So this distance here is the actual error between the actual value of x and the approximated value of x using the equation of the tangent line. For part B, the directions are the same. We want to find delta y and then dy. So delta y, we take f of x plus delta x minus f of x. So we have f of negative 2 plus 0.4 minus f of negative 2, and negative 2 plus 0.4 is negative 1.6. And if we take our function f of x, 6 minus x squared, and evaluate f of negative 1.6, and evaluate f of negative 1.6, we get an answer of 3.44, and then f of negative 2 is equal to 2. So delta y is equal to 3.44 minus 2, which is 1.44. Now to find dy, we take f prime of x times dx, and remember dx is the same as delta x. So f prime of x, if we find this on the bottom of the screen, is equal to negative 2x, and so f prime of negative 2 is equal to 4. So we have 4 times 0.4, which is equal to 1.6. So dy is equal to 1.6. So on the graph, our x is equal to negative 2, and the y-coordinate that corresponds to it is right here. And since our x is negative 2 and delta x is equal to 0.4, when we add these two together, we get negative 1.6, which is right about here. And the y-coordinate that corresponds to it on the function is right about here. And the y-coordinate that corresponds to the tangent line is right about here. The distance from the tangent line to x equals negative 2 is dy, and the distance from the function to x equals negative 2 is delta y. So you can see that there's a difference in values right here if you were to So this distance right here is the difference between delta y and dy. For number 3, find dy. The examples in number 3 For number 3, we are also asked to find dy. But on each of the parts in number 3, we are just given a function. So when you're asked to find dy and you're just given a function, you want to use the notation of finding a derivative dy dx. So that when you take the derivative dy dx, it's equal to 3x squared minus 3. But because we're asked to find dy, we take dy For number 3, we're asked to find dy, but this time we are just given a function, y equals x cubed minus 3x. So we just want to find the derivative, but the notation that I will use is dy dx. And dy dx is just another way to write f prime of x. And we have 3x squared minus 3. And since we just want to find dy, I'm going to multiply both sides by dx so that the dx's cancel, and I'm left with dy equals 3x squared minus 3 times dx. For part B, once again I'm just given a function and I want to find dy, so I start with dy dx, and this derivative just requires the quotient rule. So I have 2 times 1 plus x minus 2x times 1 over 1 plus x squared, which is 2 plus 2x minus 2x over 1 plus x squared. And instead of writing dy dx equals, I just write dy equals 2 over 1 plus x squared, and I just include the dx on the right side. For part C, y plus xy equals x. So this type of derivative problem looks like it's going to be implicit differentiation. But to avoid implicit differentiation, I can factor out a y and rewrite this function as 1 plus x times y, and then divide both sides by 1 plus x, so that I don't have to use implicit differentiation, but I do have to use the quotient rule. So I start with dy dx equals 1 times 1 plus x minus 1 times x over 1 plus x squared, and I have 1 plus x minus x over 1 plus x squared, which simplifies to 1 over 1 plus x squared. And I just move the dx over to the right side, so I have 1 over 1 plus x squared times dx. For part D, y equals 4 times tangent squared of x over 2, so dy dx is equal to 4 times tangent squared of x over 2. To start with this derivative, I start with the power of 2, so that I have 8 times tangent of x over 2, and then I take the derivative of the function tangent, and the derivative of tangent is secant squared. So it's secant squared, still of the angle x over 2, but now I have to take the derivative of the angle, and the derivative of x over 2 is just 1/2. So to simplify this 2 reduces with the 8 to make it a 4, so I have 4 times the tangent of x over 2 times secant squared of x over 2. But I don't want to leave the problem like this because there is a trig identity of tangent squared plus 1 equals secant squared. And if I use this part on the left and substitute it in for secant squared, I have 4 times tangent of x over 2, and then secant squared is tangent squared of x over 2 plus 1. And I use the substitution so that I can write all of the functions as tangent. And now I take this entire function and distribute to both terms inside the parentheses. I have 4 times tangent cubed of x over 2 plus 4 tangent of x over 2. So my dy dx is equal to 4 tangent cubed x over 2 plus 4 tangent x over 2. And I just want to move the dx over to the right side. And this whole function is multiplied by dx, so I'm just going to put it in brackets. For part E, y equals x squared minus cosine of x squared. So I start with dy dx equals the derivative of x squared is 2x, and then the derivative of cosine is minus sine, but because you have a minus in front of that cosine, it changes to plus sine, and then I take the derivative of the angle, which is 2x, so I can rewrite dy dx as 2x plus 2x times the sine of x squared, and then I just move the dx over to the other side. So I have 2x plus 2x sine of x squared, and I'm just putting it in brackets to show that the whole quantity is multiplied by dx. For number 4, use differentials to estimate the given number. So when you use For number 4, use differentials to estimate the given number. When you're asked to use differentials to estimate the given number, the formula that you want to use on the very first page would be the one for approximating function values, which is f of x plus delta x is equal to f of x plus f prime of x dx. So the first thing we have to do is we have to look for a function that would apply to the square root of 36.1. And since it's a square root function, then the function f of x is just the square root of x. Then we want to find our x value that we would use, and the x value would be the closest perfect square to 36.1, which is 36, which makes our delta x equal to 0.1 because the number that we're given is 0.1 unit higher than 36, and our dx is also equal to 0.1. So I have all of the information that I need except for the derivative. So to find f prime of x, the square root of x is the same as x to the 1/2. So I have 1/2 x to the negative 1/2. And f prime of x can be rewritten as 1/2 times the square root of x. So to approximate this answer of x plus delta x, I take f of x, which is f of 36, plus f prime of 36 times dx, which is 0.1, and f of 36 is just 6. F prime of 36 is 1/12,